Namaste and welcome to this lecture on linear algebra through geometry. In the last week's classes we saw the idea of vectors in 3 dimension, where we actually looked at the idea of cross product. We looked at projection of a vector onto another vector, a line passing through that a line defined by that vector, and then a projection of a vector onto the plane passing through the origin and orthogonal to another given vector. Then we looked at the idea of the cross product of two vectors in 3D, which was another vector which was perpendicular to both vectors, and then we looked at the volume of a parallelepiped, and we also looked at generalized Pythagoras theorem, and we also did the looked at the geometry of lines in 3D, where we said lines need not be parallel. In this case, lines can be skewed. For example, you can have lines, if you look at a unit cube, you can have lines on the opposite edges, and which need not be parallel, which are probably in two different parallel planes. That is what we looked at, and then we also looked at the idea of intersection of line and plane. We found the point of intersection between a line and a plane. In this week we are going to look at linear maps in 3D. We are going to visit revisit our ideas of reflection, scaling, rotation, shear, and all those things which we did in 2D. We are going to look at 3D. There may be something we will see that the idea of shear, the idea of what we call rotation, and all those things being different in 3D. There are different aspects to it, is what I mean. We are going to have that, and then we are going to look at the idea of volumes, and we are going to interpret the volume to be the determinant of a 3 by 3 matrix, and we are also going to look at the idea of eigenvalues and eigenvectors in 3D. So that is the agenda for the week, and so we start with linear maps in 3D. So we are going to look at linear maps in 3 dimension. So we are going to look at linear maps in 3D. What is it to say a linear map? We already know it from 2 dimension, where we said that okay, how does a vector in 2 dimension get transformed to another vector, and we looked at some of them, which includes scaling, reflection, rotation, and projections. These are things that we looked at in 2D. We are going to follow the same sequence here. So, we are going to look at the idea of scaling in 3D, and then go ahead. Yeah. So, let us look at that. So, what does scaling do? We already know that scaling basically it is a map, it is a linear map that enlarges or shrinks a vector, that enlarges or shrinks a vector. So, if we take V to be a vector, let V be this vector with 3 components, V1, V2, V3, and let V dash be this vector, let V dash be this vector, which is given by V1 dash, V2 dash, and V3 dash, which is the same as this, let us say S times V1, S times V2, S times V3. right. Now, which means I am going to where S is a scalar, where S is a scalar. So, the question that we ask is what is the matrix which is going to scale a given vector to get the scale version of the vector, say V1 the vector V. So, what we have? We have V1, V2, V3, and here we are going to look at SV1, SV2 and SV3. This is going to give an equal scaling along the direction, let us say the E1 direction, E2 direction, E3 direction, where E1 direction is basically the 1 0 along the direction of 1 0 0 vector, E2 direction is along the direction of the 0 1 0 vector, and E3 is the direction along the 0 0 1 vector. So, what is the matrix which does this? So, if you clearly see this, this is just going to be the identity matrix with the diagonal elements replaced with S. So, if we say that if S is going to be depending on the value of S, we are going to have either it is the vector is going to be shrunk or the vector is going to be enlarged. Now, the next question is, can we have different scaling along different directions? Yeah, that is of course possible, for which we are going to say that let us look at this. For example, I have this vector, say same vector V1, V2, V3, the V vector. Now, what I am going to have is, suppose I say that I have this S1 V1, S2 V2 and S3 V3, where S1, S2 and S3, S1, S2 and S3 are scalars. So, S1, S2, S3 need not be equal. So, in that case, what is the matrix which is going to do this? We are going to see that this matrix replace the diagonal elements of the unit matrix or the identity matrix with the values S1, S2 and S3. So, this is the matrix which does the scaling of the vector with different scaling factors along different axes. So, we say that if a specific SI, where I is 1, 2 or 3, a specific SI is such that 0 less than SI less than 1, then we get a shrink. We get a shrink along the ith direction, in that direction. Suppose let us assume that let us consider this. For example, we have this, we have the matrix which is going to be S1, which is let us say 2 0 0 0 0.5 and 0, and we have 0 0 minus 1, and that is going to transform this vector V as 2 V1, 0.5 V2 minus V3, right. So, what are we going to say? How are we going to interpret this? It says there is a stretch. So, this implies the interpretation is there is a stretch along the S1 direction or the stretch along the E1 direction, then we are going to have a shrink along the E2 direction, and this negative 1, it says V 3, it now becomes minus V 3, that means we are going to have a flip along, we are going to have a flip along the E 3 direction. I hope we recall the E1 E2 E3 directions as E1 is equal to 1 0 0, E2 is equal to 0 1 0, and E3 is 0 0 1, right. Yes. Now the question, so suppose we have this, let's have this question. So suppose I have a unit cube. We have the unit cube defined by the E1 E2 E3 vectors. We have the unit cube defined by the E1 E2 E3 vectors, namely 1 0 0, 0 1 0, 0 0 1. We know that the volume of the unit cube, the volume of the unit cube is given is 1. Then the volume unit cube is 1 cubic units, it is 1. Now if I apply scaling in each of these directions, how does the volume change, right. Suppose I scale the E1 direction by S1 and E2 direction by S2 and E3 direction by S3, how does the volume change? So that is a question that we ask. So what we do is with a scaling factor, so with a scaling factor, let us say S11, S22, okay, with scaling factors, with scaling factors S11, S22 and S33, we have the unit cube to get transformed to, we have this 1 0 0, 0 1 0, 0 0 1, that gets scaled by this S11, 0 0, 0 S22, 0 0 0 S33. We basically get this, which is S11 0 0, 0 S22, 0 0 S33. So what is the volume of this resulting cube? So the new volume is going to be the following. So the new volume is basically the product of the scaling factors. New volume is equal to S11, S22, S23, the product of this S11 into S22 into S23, right. That is basically because the new length along the E1 E2 E3 axis are S1, S2 and S3, S11, S22 and S33. So the product of these three is going to give the new volume, which means we are going to say that the scaling, if you do, whenever you do scaling, we say that the scaling changes, scaling changes the volume of an object, the volume of an object by a factor equal to the product of the scaling factors. Of the scaling factors. Yeah. So that is interesting. So if you scale, then the new volume is going to be the new volume is going to be scaled by the product of these scaling factors that you have used, right. Okay. Now, what was the next linear map that we studied, linear transformation that we studied in 2D? That was basically the reflection. So, let us look at that. So, we are going to look at reflections in 3D. We are going to look at reflections in 3D. It is interesting to recall that when we did reflection in 2 dimension, we actually looked at reflection about a line passing through the origin in the direction of say some vector u which is given by u1 u2, right. Whereas in case of reflections in 3D, it could be reflections, it could be a reflection about a line passing through the origin, or it could be a reflection about a plane passing through the origin. So, these two things, I mean the one more thing that comes into picture compared to the 2 dimension is the reflection about a plane, right. So, we will look at both of them now. We will also try to get some good insights about reflections that happen both in 2D and 3D. Okay. So, let us first look at the idea of reflection in 2D to understand geometrically a bit, and then we go to the idea of reflections in 3D, right. Okay. So, let us look at that. So, reflection in 2D, if we recall, reflections in 2D were about a line passing through the origin, lines passing through the origin. So, in 3D, reflections can be about a line passing through the origin, about a line passing through the origin, or a plane passing through the origin. Right. So, let us consider one by one. So, we will look at reflection about a line passing through the origin, for which we will first look at reflection in 2D in a slightly different form than what we did in our 2D. So, when we did our lectures on 2D, so here what we are going to do is we are going to generalize this reflection about a line passing through the origin in 2D. We will try to take the same idea to reflections about line passing through origin in 3D, right. Okay. So, let us look at this. I am going to do this. So, reflection in 2D, this is what we are going to look at. So, let us define a few things. Okay. Let RF denote the map that assigns to every vector let us say x, the reflection of the vector x in the line along the vector u, in the line along the vector u, which is let us say u1 u2. So, we have the vector x which is x1 x2, we are looking at 2D in the first place, and we are going to take the vector u to be u1 u2. Now, let us see what is actually happening. For example, we have this. So, here is your 2-dimensional plane, your xy plane, whatever we have. So, let us look at that. Let us assume that this is basically the vector, say u, which is u1 u2 u2, and let us look at this vector. This vector is basically let us say x1 x2, right. Now, what we want is we want a reflection about this, which means this is going to be here, so this is going to be the reflection of the point x, the vector x or the point x about the line passing through the origin defined by the vector u. So, this is going to be my let us say RF of x, where RF of x denotes the reflection of x. Okay. So, let us look at this. So, what does it mean? So, we are going to say the following. So, let RF of x be the point such that the midpoint of the line segment joining x and RF of x, x and RF of x is the projection of x, is the projection of x vector to the line along u, right. Let us call this projection that we have along u, let us call that as p of x along the direction u. So, you can put p u, which says that it is along the direction of u, or just leave it as p of x, that is a notation that we have used before. So, we use p of x. Yeah. Now, what we see is so what is the so what does it say? The point p of x is basically the midpoint of the line segment joining the vector x with RF of x. So, I am going to write p of x is equal to, it is half of, you recollect we did this in 2D when we did the what you call the barycentric combination, and we looked at the convex combination of points, we actually looked at this. So, I am going to look at p of x is equal to half of x plus the reflection of x, RF of x, this is what I am going to have. Now, which implies RF of x, reflection of x, is nothing but 2 times the projection of the vector x along the direction of u, that means it is projection of x on the line defined by the vector u, minus we have the x vector. So, this is going to be my reflection transformation, right. That is going to be the reflection of a point about a line passing through the origin. This is going to be in 2 dimension, right. This is going to be in 2 dimension. We can take a simple example quickly and then check if this actually holds. For example, let us look at the okay, let us look at this example. Okay, I will do it in the okay. example, let us consider u to be the vector 1 1 and let us take x to be the vector 2 3. The point 2 3, I want to look at the reflection of this point 2 3 about the line passing through the origin and in the direction of 1 1. So, how did we define this? We know that RF of x, we said this is equal to 2 times the projection of x along the direction of u minus the vector x. Now, what is projection of the vector x along the direction of u? We already know this. This is nothing but x dot u divided by u dot u in the direction of u, and we have minus x vector. Oh, sorry, in the direction of u, that is what we are going to have. So, let us see what it is. So, that is going to be u transpose x divided by u transpose u in the direction of the vector u, which is nothing but let us say 1 1 into 2 3 1 1 dot product with 2 3. So, it is going to be this divided by 1 1 1 1 along the direction of 1 1, which is nothing but 2 plus 3 we have so yeah we have 2 plus 3 which is 5 divided by 2 in the direction of 1 1. So, that is going to be 5 by 2 5 by 2. So, this is the projection of the vector along the line in the direction of u, and what we have is, now we want to find out the reflection of this particular point x, which is given by 2 times p of x minus the x vector. 2 times p of x is basically 2 into 5 by 2 5 by 2 minus the vector that we have is 2 3, that is the original vector. So, this is going to be 5 5 minus 2 3, which is basically 3 2, and that is something which we have already seen reflection about. This is basically the vector basically defines the line passing through the origin, and the line is characterized by y is equal to x, the equation y is equal to x. So, basically if you look at this graphically, this is what is going to be. So, assume that this is my x1 x2 axis. I have this point 2 3, let me mark 1 2 3 4 5 1 2 3 4 5 and so on. So, 2 3 is basically here. So, 2 3 is this vector. So, 2 3 is basically this vector, and we have this line passing through the origin and through 1 1 is basically this is the direction 1 1, and what is the vector that we get? We basically get 3 2, which is basically here. So, this vector is here. So, this is the original vector we had, and this is the reflected vector, the reflection of those vectors. So, it is also easy to see that if you want to reflect above this particular point, all we need to do is we need to swap the rows, which is basically 2 3 becoming 3 2. Now, what happens in 3 dimension? We can extend the same idea to 3 dimension also. So, we extend the same idea in 3D2. So, we are going to say extending the same idea we have the reflection, which is basically reflection of a point x about a line passing through the origin and in the direction of, let us say, a vector u. So, reflection of x where x vector is this, and reflection about the line through the origin through the origin and in the direction of the vector u, which is given by u1, u2, u3. So, what are we going to have? We are going to extend the same thing there. So, I am going to say R f of x, we have let us say the reflection of x, R f of x. R f of x is given by 2 times p of x minus the vector x itself. Okay. For example, so this is going to be the case. We can look at an example. We have, let us say, the vector x is going to be 1, 2, 3, and let us look at the vector u, which is 1, 1, 1. Then we already know what is the projection of this vector x along the direction of u. So, that is going to be so we are going to look at p of x. P of x is nothing but x transpose u divided by u transpose u in the direction of u. So, I am going to get 1, 2, 3, 1, 1, 1 divided by 1, 1, 1, 1, 1, 1 in the direction of 1, 1, 1, which is going to be 1 plus 2, 3 plus 3, 6, 6 by 3 is 2. So, I am going to get 2, 2, 2 is what I have. Now, therefore, what we have is we look at the reflection. So, R f of x is nothing but 2 times p of x minus the vector x, which is nothing but 2 into 2, 2, 2 minus 1, 2, 3, which is basically 4 minus 1, which is 3, 4 minus 2, which is 2, and 4 minus 3, which is 1. So, this is basically the reflection about. So, this is basically the reflection of a point about a line passing through the origin. So, the next question that we have is question. So, what is the reflection of a point? What is the reflection of a vector or a point about a plane passing through the origin and orthogonal to u, orthogonal to some vector, let us say the vector u, which is equal to u1, u2, u3. So, how is this going to be different from the thing that we had for reflection about a line passing through the origin? Is it going to be the same or is it going to be different? If it is different, how is it different? If it is the same, then what is the difference between saying reflection about a line and reflection about a plane passing through the origin? This is something which we will explore in the next lecture. Thank you.